Los estudiantes que postulen para la maestría en geotecnia aplicada tienen una gran ventaja de que se busca hacer una vinculación entre el conocimiento de la geología y la obra civil. El objetivo que se pretende es que los maestrantes obtengan un mayor conocimiento teórico-práctico sobre lo que es el sistema de construcción, diseños de construcción, para hacer obras seguras más sustentables y mucho mejores en la región. El estudiar la maestría de geotecnia aplicada en la UTPL es una gran oportunidad en este momento, dado de que es la primera maestría profesionalizante que se oferta en la región sur del país. Entonces, esto es un gran incentivo para los profesionales, tanto de la geología como de la ingeniería civil, para adquirir mayor competencias y mayores conocimientos en el campo de la geotecnia y de las obras civiles al mismo tiempo. A ti que eres ingeniero civil, ingeniero en geología, ingeniero en minas y arquitecto, te invito a que seas parte de esta maestría en geotecnia aplicada que oferta la Universidad Técnica Particular de Loja.
Se acompañan esta tarde. Nos encontramos realizando nuestra última conferencia de este mes de mayo y gracias a esto tenemos a nuestro invitado especial e internacional, el profesor Richard Spicki. Como ustedes conocen, nos encontramos también festejando los 50 años de vida institucional de la UTPL. Además, este 29 de mayo cumpliremos 36 años de creación como carrera. Nacimos como una tecnología, hoy somos una ingeniería y ofertamos también maestrías. Cada día vamos mejorando y ampliando nuestros horizontes. Por ti, para brindarte una oportunidad, contamos con laboratorios de vanguardia de mecánica de suelos y rocas, beneficio de minerales, geoquímica, petrología, paleontología, fotointerpretación, modelos analógicos de deformación, perforaciones y logueo, geofísica y laboratorios virtuales. Además, dentro de nuestra carrera se realizan prácticas de campo para acercarte a un entorno real. También te enseñamos diferentes tipos de softwares para modelar como Move, Promine, StereoNet, Foldskin, Snap, FoldFold, Visible Geology, Petrograph, Global Mapper, SIG, entre otros. Estamos en constante cambio y formación para brindarte los mejores conocimientos para tu futuro laboral. Contamos con 4 PhD, 3 en formación, 10 másters y somos un grupo de docentes innovadores. Nos preocupa la vinculación social y la investigación. Nos transformamos para que tú seas más. Te esperamos. El éxito depende de la preparación previa. Cuenta con nosotros para alcanzarlo. Esta tarde, como ya les había mencionado, contamos con la presencia del profesor del PhD, Richard Spicki, quien es profesor de la Universidad de Génova, quien nos hablará sobre Geochronology and Tectonics of the Cordillera Real, Ecuador. Welcome, dear professor. Bienvenido, le agradecemos por participar esta tarde. También me acompaña en esta tarde John Manrique, quien dará lectura sobre la hoja de vida resumida de nuestro ponente. Bienvenido, John.
Gracias, Verónica. Bienvenidos de nuevo a todos los compañeros que están asistiendo a las conferencias. Voy a proceder a leer de manera corta el currículum del Dr. Richard Spicki. El Dr. Richard Spicki es graduado como primero en su clase con honores en la licenciatura en Geoquímica de la Universidad de St. Andrews en Escocia y realizó sus estudios de doctorado en Ciencias de la Tierra en la Universidad de La Trobe en Melbourne, Australia, y su trabajo fue titulado Termocronología y Tectónica de los Montes Isa, Murphy and Georgetown Inliers en el oeste de Australia. Actualmente, como lo mencionó Verónica, se encuentra trabajando como profesor investigador senior en la Universidad de Ginebra, Suiza. Se ha especializado en la termocronología. También ha trabajado como postdoc en la Universidad de Ginebra y en el Instituto Federal Suizo de Tecnología de Zurich, el ITH, También hizo un postdoc en la Universidad de Potsdam, en Alemania. Sus últimos logros científicos a lo largo de los últimos 5 años se basan en la termocronología de altas temperaturas, así como la síntesis de la tectónica de los Andes del Norte y el Caribe, además de investigaciones en la Antártica. Bueno, para nosotros es un gusto, un placer contar con Richard en nuestras conferencias. Richard, can you start your talk?
Okay, I will share my screen. Just one moment. Is that okay?
Yeah, it's
It's okay.
Okay, so first, thank you very much for the kind introduction. I'm very grateful to UTPL to invite me to give this talk. Thank you, Professor Manrique, for the invitation. I'm very happy to be here. Wish I could be in Ecuador, but of course it's not possible at the moment. So I will talk to you about the geochronology and tectonics of the Cordillera Real. In fact, I will talk about more than just this. I will also talk about geochemistry, isotopic tracing, and thermochronology. So it's not just geochronology, but it's mainly based around isotopes and geochemistry. And also, I will focus on the Cordillera Real, but I will also talk about the Cordillera Central in Colombia, because it's the same thing. And I will explain that now. So, all right. So a map, obviously, of Ecuador and Colombia. So just for your reference, this black line here that runs up here is the approximately 75 million year old ocean continent suture. So everything to the west, in the western Cordilleras of Colombia and Ecuador, and in the Forac, this is all accreted oceanic lithosphere, 100 to 90 to 80 million years old, more or less, before it accreted. And everything to the east of the suture, the Cordillera Real and the Cordillera Central in Colombia, this is all early Cretaceous and older, more differentiated continental crust. So this big black line is an ocean continent suture. It's Campanian, about 75 million years old. So I will talk about the rocks just proximal to this suture on the continental side. And so I'll speak mainly about the Cordillera Real here, but I'll also speak about the Cordillera Central a little bit because, as I said, the rocks are equivalent and the history is extremely similar. And I'll also talk a little bit about the Santander Massif and the Sierra Nevada de Santa Marta because they're all linked together. So it makes sense to talk about them together. Okay. So I will speak about the period between the Permian to the early Cretaceous. Okay, we only have 45 minutes, so that's all we can really cover, but it's already a lot. So first of all, this map, this is the British survey map of the Cordillera Real in Ecuador. There's the frontier with Colombia, and this is the Cordillera Central from Inhumenes in Colombia, right? So they're just drawn as one map here. And this black line here is this ocean continent suture, which I mentioned before, this Campanian suture. So first of all, the Permian, well, the Permian is essentially, the igneous record is essentially just a series of foliated granodiorites. And all these numbers here are concordant uranium-lead zircon dates. And the Permian rocks are in these purple colors. So the southern and central part of the Cordillera in Ecuador and mainly around Antioquia in Colombia. And in fact, in Colombia, here you can see some example dates, 278 million, 276 million. And actually, in fact, in Ecuador, there's only one rock. That's really right down here by Malacatos, 283 million. So actually, we gave it the name, the Malacatos complex. So actually, in Ecuador, there's only one Permian igneous rock. So I won't talk about this a lot, but it's important that we don't forget it. But then when you go into the Triassic, we have a fundamentally different series of igneous rocks in the Triassic. They are bimodal. So what you can see in these photographs, this is the acidic end member of the Triassic bimodal units. And this is the Sabinia migmatite and the Tres Lagunas granite here. So the Triassic acidic rocks are these leucosomes. For example, the white phases here. And sometimes these leucosomes have joined together to form these larger plutons of the Tres Lagunas. Of course, Sabinia, Tres Lagunas, there's a lot of this down by Loja. And all of these Triassic dates here that are not Permian are from these acidic rocks. But there's also a mafic Triassic end member, which is essentially amphibolites, bimineralic plagioclase hornblende amphibolites, which occur as dikes and sills. And I'll talk more about the mafic end member in a minute. So here's a compilation of those crystallization ages on the y-axis against the latitude. So from northern Colombia here to the Peruvian border of Ecuador down here. So for the Permian, we just see these a very small amount of igneous rocks. They're mainly granodiorites. They're mainly in Colombia. There's only one in Ecuador. But for the Triassic, we have this bimodal acidic and mafic sequence. The acidic are the pink colors, the mafic are the blue colors. And the main point to get from this slide is when we go from northern Colombia to southern Ecuador, there's no change in the age. The ages are more or less the same everywhere in Colombia and Ecuador, all right? And it's kind of early to middle Triassic, this igneous sequence for the Triassic. Now, I've also shown you here various different regions in Venezuela, the Merida Andes, Paraguana, El Bao, Eastern Cordillera of Peru, and different terrains in the southwestern part of North America, mainly in Mexico, Guatemala. And this is just to show you that we have igneous units of these ages also in these regions. I don't have time to talk about this at all, but this is important when I show you the plate reconstructions. So bear in mind that very similar rocks are also exposed here. So again, staying with the Permian and the Triassic units and the geochronology, the crystallization ages, is a histogram, so frequency of the weighted mean ages. So a frequency of 1 is the age of one rock. So there's the Permian units in Colombia and Ecuador. The pink is Ecuador, only one Permian. And here's this big Triassic mass of rocks in Colombia and Ecuador. This is a similar diagram. It's a histogram. But here, what I've dated, so these are also uranium-lead dates here in a histogram format. And these are the xenocristic cores, the inherited cores in the Triassic and the Permian units. So what you see is a big peak here at kind of Brasiliano type ages and a big peak in Sunsas type ages. So this is just to show that clearly these units are derived from Gondwana. The rocks which melted to form the Triassic and Permian units were part of Gondwanan crust because this is a Gondwanan signature. So what about the tectonic environment where the Permian and the Triassic igneous rocks formed? Well, so to look at that, we can look at the chemistry. So here we have some millication plot. It doesn't really matter what these are, just a geochemical plot, which is the lithological discrimination. That's all that's important. The blue is the Permian, and these pink colors are the Triassic. And these are all these acidic end member units. So for the Triassic, it's the Sabinia and the Tres Lagunas, okay? Along with the Permian in blue, the granodiorites, mainly. So first of all, for the Permian, we can see we get a fairly continuous sequence from granodiorites up to gabbros. For the Permian, the blue colors. But for the Triassic, even in the Sabinia and the Tres Lagunas, it already looks kind of bimodal. We have these granodiorites, mainly granodiorites, then a gap. There's nothing here, and then some gabbros. Okay, so the Permian look a little bit different to the Triassic. The Permian have a continuous sequence. The Triassic looks bimodal. In this plot, we see that both the Permian and the Triassic igneous units are mainly calc-alkaline to calcic, but the Permian in blue become a bit more alkaline than the Triassic. Now, these two plots are very important. So this is what's called the aluminium saturation index. Doesn't really matter. What's important, of course, is what it's telling us. And what it's telling us is, first of all, for the Permian in blue, these are quite metaluminous. They go here. This is classic arc. The Triassic in pink are very, very periluminous. And this information for the Triassic combined with the stable oxygen isotopic compositions in quartz, which are, this is actually very high numbers. So the very high, what's called delta 18O values for the Triassic, and the highly periluminous for the Triassic suggest that the Triassic, the Sabonia leucosomes, and which come together to form the Tres Lagunas sometimes, are melts of sedimentary rocks. These are metapelites. So that means the next question is, what was the heat source in the Triassic that was melting the crust? Where was the heat coming from? What was melting the pelites? Some trace elements, both for the Permian in blue and the Triassic in pink. So mid-ocean ridge normalized. I'm not going to go into great detail here, just to say that this topology, this form with the negative niobium anomalies, negative strontium, negative titanium, looks like classic arc related, or related to dehydrating a subducted slab. And in fact, for the Permian in blue, this is the conclusion. These are arc rocks. But this signature can also be obtained by just melting the crust, because of course the crust also has an average arc andesitic composition. And in fact, when you normalize the Permian and the Triassic compositions to upper continental crust, they plot close to 1. So in fact, the Permian and the Triassic rocks are the consequence of melting continental crust. But the difference for the Triassic is they melted sedimentary units. Okay, even though the Triassic and the Permian are derived by melting crust, the Triassic was specifically melting the sedimentary part of the crust. Okay, this is the rare earth element plot, again for the Permian and the Triassic in pink, the Permian in blue, enriched light rare earth elements compared to heavy. This is just supports what we see here, that these are crustal melts. And this is a very important plot, because this plot has the lanthanum-ytterbium ratio. And what that is really is just the gradient of this plot. So smaller values here mean flatter lines on this plot. And what we can see, here we have this ratio compared with the crystallization age. What we see for the Triassic, 250 to 210 at least, is this value, generally speaking, gets lower as we go younger through the Triassic. And we interpret this to be because there's increased amounts of partial melting. So remember, the Triassic are melts of sedimentary rocks, and the amount of melting was increasing through the Triassic. So the heat source, whatever it was increasing through the Triassic. But these are important clues to tell us what was the tectonic environment. So staying again with the Permian and the Triassic, for the Permian in blue, just potassium oxide against silicon oxide. Again, the Permian, we see a fairly continuous sequence in silicon oxide. It's not bimodal, but the Triassic in pink is very bimodal, right? All the chemistry I showed you here was for these units. But now we're going to look at the chemistry of these mafic Triassic dikes and sills, which today are actually amphibolites, like the Piedras or the Monte Olivo, for example, in Ecuador. So the hornblende plagioclase rocks, but what was their original mineralogy? Well, first of all, they plot here in this discrimination diagram in the subalkali basaltic field. They were certainly basaltic, doleritic, basaltic. Anyway, they are dikes and sills. And what this diagram is important. The details, don't worry about the details. It's vanadium, titanium. It doesn't matter. What's important is these mafic rocks mainly plot here, and this is an extensional field. Mid-ocean ridge or back arc basin, an extensional field. So Triassic is bimodal magmatism in extension. This is a rift. Rifts do this. And when you look at the mafic units, the trace elements normalized to mid-ocean ridge, they're flat. This is melting of depleted mantle. The rare earth elements are fairly flat, normalized to MORB. They look like MORB. except they are slightly enriched. So these are melts derived from the depleted mantle, which have been contaminated with a little bit of crust. That's the mafic end member. Because we are building the jigsaw, we must put all this together. This slide is very useful, very powerful. So what we're looking at here, we're still talking about the Triassic and the Permian, but this slide focuses really on the Triassic, okay? What I've plotted here is what's called epsilon hafnium. So this is the composition of the hafnium isotopes in zircons in the Triassic rocks, in these pink rocks in this diagram, in these rocks. So zircons out of the Sabinia, leucosomes out of the Tres Lagunas. What's the hafnium isotopic composition, right? And the way to understand this is high values means that there was a very strong crustal component in the source of the magma. Sorry, low values, excuse me, mean there was a very strong crustal component in the source of the magma, and high values mean there was a very strong mantle component. So what's important to focus on in this graph, right, is these pink diamonds here, which are all surrounded by this gray field. These are all the Triassic rims in the zircons in the Sabinia and the Tres Lagunas. Okay? So what they show is it's crustal. These are low values. These are derived from the crust. In fact, I already told you this from the chemistry. In fact, they are derived mainly from melting sedimentary rocks, the acidic end member for the Triassic. Now, if you go to the blue here, the blue colors, these are zircons in the mafic rocks, in the mafic dikes and sills, which are Triassic. And this is very, very important. So here, this graph is just a magnification, the same graph, hafnium and uranium lead, but for the mafic. And in fact, I've shown you data from 4 rocks here, these dikes and sills, the Triassic mafic dikes and sills. The way to read this graph is this is all data from one basalt, one hand specimen. The age of the basalt is around 232 million. And these are all the analyses of individual zircon crystals in that basalt, which have different hafnium measurements, right? So these zircons have a high hafnium measurement. These zircons have a low hafnium measurement. So what does this graph tell us? Well, it tells us that these 2 basalts at 232 and 240 million have some zircons which were derived from a mantle source, but there are some zircons in these rocks which are derived from melting the crust. So that tells us that these mantle-derived melts were being contaminated with crust. In other words, there was some crust present to contaminate the mantle-derived melts. But when you go younger than 225 million, the dikes and the sills in the Triassic don't have any zircons, nothing, which form from melting the crust. In other words, it's all the melt is from depleted mantle. There was no crust present to contaminate the mafic melts. So remember, this is extension. It's probably a rift. So this is the continent becoming thinner and thinner and thinner. And after 225 million years, there's no crust left to contaminate the mantle melts. This is a rift to drift transition. So to summarize this, because it's quite a lot of information, so here we've got time from the Permian, Triassic into the Jurassic. Here is the acidic rocks and some mafic rocks, okay, amphibolites and the anatectites. This is the Sabinia and Tres Lagunas. This is the Monte Olivo, for example, from Ecuadorian terminology. So for the Permian, first of all, so in the Permian period, we have many, many rocks. They're only really mainly granodiorites. There's nothing here because there's no mafic end member for the Permian. So all the data is here in the acidic field. And in fact, they are arc. I don't talk about this very much because there's only one rock in Cordillera, in Ecuadorian Cordillera, which is Permian. But it was an arc. And we know from work in Colombia that this arc underwent a strong compressive event, a Barovian metamorphic event at 255 million, okay? But that evidence is not present in the Cordillera Real, but it is in Colombia. But when you go into the Triassic, suddenly all the mafic rocks appear, as well as the acidic rocks of Sabinia and Tres Lagunas. Is bimodal, and this is certainly a rift. So it's fundamentally different to the Permian. So what we see is, so if you remember the lanthanum and terbium ratios, what this shows is in the anatectites, in the Sabinia, in the Tres Lagunas, which formed by melting sedimentary rocks, that the partial melting was increasing. The heat, which was heating the crust, was increasing through the Triassic. It was getting hotter and hotter and hotter, which is characteristic of a rift. The crust was just getting very hot and it was melting, forming the Sabinia and the Tres Lagunas. And in the mafic units, in the isotopes of hafnium and neodymium, these trends that we see, I'm not going to explain them again, show that with time, as the continent was becoming thinner, the mantle-derived melts were being contaminated less and less and less by the continent because it was getting thinner and thinner. This is again characteristic of a rift. And we end at 216 million years with the age of a plagiogranite just to the south of Medellin, which forms part of a coherent ophiolite at 216 million. So this is a full rift to drift giving rise to ophiolites. So this is actually a fantastically well preserved. It's one of the best preserved Mesozoic rifts on Earth. It's a full rift to drift transition. So to summarize this, for the Permian, so you see the Permian period, but a very, very, very well-established subduction zone. So we even have the Permian continental arc rocks preserved in the southern eastern Cordillera of Peru. In the Cordillera Real, we only have one. That's this blue, that's this red V here near Malacatos. In the Cordillera Central and this Sierra Nevada Santa Marta in Colombia, we have a few more. But basically, Colombia and Ecuador were in the Permian back arc, which is why you don't have very many Permian, because you were in the back arc. The arc was in the Chortis, Acatlan, Maya, and this thing I can never pronounce, Oaxaca or whatever, which now forms southwestern North America. At 255, these collided, and these M indicate where metamorphic zones have been identified and dated. So there's a compressive event at this time, which is not registered really in Ecuador because you only have the one rock anyway. There's not enough material to find evidence for this in Ecuador, but it's clear in Colombia and clear in Yucatan, the Maya block, and in the Chortis block. So now when we go to the Triassic, in the Triassic, a rift forms here in a back arc. So there's a back arc rift. So here's Z, Z prime, Z, Z prime. Okay. So here in the beginning of the Triassic, we have the Permian slab. So here's the old Permian arc, which rifts off now in Mexico, mainly. In the back arc, we have this simple shear extensional system, probably already forming or melting sedimentary units, that's these pink colors, by frictional heating. As we go further into the Triassic, extension continued. There must have been continued trench retreat or rollback, continued tension here, extension, upwelling and decompression of the mantle, causing melting. And that's when you bring in these blue colors, which are the basaltic dikes and sills, the mafic end member for the Triassic. And these bring in a lot of heat into the crust, which drives more melting of the crust, more and more partial melting of the crust. So this is the heat source, decompression of the mantle due to rollback. And by 216, we have the ophiolites in Medellin, a full rift to drift transition. So now let's go on to what happens next. In this diagram, I had actually the Jurassic up here. And actually, after the rift and the rift to drift is probably a passive margin for a short time, it becomes active again. So now I'm going to talk about this period, the Jurassic into the early Cretaceous. Looks like a very complicated map because there are many, many dates, and most of these dates are zircon, uranium, lead, Concordia dates. So I'm going to go through this quite in a very concise, summarized fashion to save time. So in the red colors, so all the way up the eastern side of the Cordillera Real, eastern side of Cordillera Central, and the Santander Massif in Colombia, which is this actually, but the colors are not here on the inset. Santander Massif, we have a whole series of continental, classic continental arc acidic intrusions, mainly granodiorites, not very deformed, only deformed near fault, so fault foliation, but no regional foliation. High potassium calc alkaline. In terms of dates, the oldest between 209 and 196 are in the Santander Massif. Then we jump across into this ridge where they go from 189 in the Sierra Nevada San Lucas in Colombia to 145 in the Zamora, and many, many, many dates in between. Okay. Now, when we go to the west of the red arc, which in Ecuador, of course, is Rosa Florida, Abitagua, Zamora. When we go to the west, we go into these blue rocks, which is also a continental arc. It's the Azafran. So in the Azafran, it's also a continental arc. These are the uranium-lead dates. It's a little bit younger than the red arc on this map. It's also a little bit less fractionated. It's more mafic, and it's got a stronger component of a mantle source in the magma source. And this is best exposed in Ecuador. There's only a very small exposure by Ibagué in Colombia. Now you go west again into the green. This is the Alau in Ecuador and the Quebrada Grande in Colombia. This is more complicated, but this is also a continental arc. Sorry, an arc. The same as the red rocks, the same as the blue rocks, the green is also an arc. In fact, it's also a continental arc. I will prove that in a moment. This is mainly mafic volcanic. So this is also, we believe, or we think, it's also younger than the Azafran. So it's getting younger to the west. We think it's younger because we dated it in Colombia. In Colombia, it's 113. You can forget this, ignore this. It's 113 to 114 million in Colombia. But in Alau, even though we tried for 20 years, we can't date it. We're having a lot of difficulty to date this. We have a master's student from EPN here now trying to date it. It's very difficult. But we think it's probably 120 million. That's a hypothesis. So therefore, it's younger. It's younger than the red rocks and younger than the blue rocks. It's 120 million. It's also more mafic, and it's got a very strong mantle component in the source. So to summarize that, when we go from east to west, from the red arc to the blue arc to the green arc, they get younger, they get less differentiated, and there's a stronger mantle component in the source. Here's a histogram of those dates of the arc units. So here's the geochronology, the crystallization ages, and the frequency. So we see we have this big late Triassic, because in the Santander Massif, it's actually late Triassic. We have this late Triassic to Jurassic, so Zamora, Abitagua, Rosa Florida in Ecuador, and then these younger early Cretaceous dates. Okay, this is the post-Triassic rift history. Now here's a simple map section from Baños Puyo across the Cordillera Real. And this is around Alau. So this is Baños Puyo, and there's Alau close to Guamoti down here. That's these aerial map sections here. And these are the same colors. So this is Abitagua, this is Azafran, this is Alau. These are the same colors as what I described on this map. And what you can, and here I've identified this line here, Peltatec fault. I've called it a suture. I don't have time to talk about why I call it a suture, but for now we call it a suture, or the location of the paleo trench for these arcs. This is the distance from the Peltatec fault or from the suture. Okay, so the distance going this way, like this, against the crystallization age of these igneous arc units. And so you can see when you get closer and closer and closer to the suture, they get younger and younger and younger and younger. All right. This is very important because the only way you can explain this through this whole period is extension. This is not slab dip change because the time period is far too long. This is extension through the Jurassic and particularly in the early Cretaceous. All these arcs formed in a period of continual extension. So let's now focus mainly on the red arc units and the blue. So Abitagua, Zamora, and the Azafran. Okay, this is the distribution of those dates. You see the time axis here, again with latitude, so from Colombia to Peru, southern Ecuador, the Peruvian border. And it looks like the dates actually do get younger to the south. I think that's an artifact because when you take more and more samples in the same latitude, for example, in Colombia by Ibagué, you find that they actually span the whole Jurassic. So if we took more and more samples in the Abitagua, I would imagine that they would start to cover the whole Jurassic. I think this is an artifact. The main trend in these Jurassic dates is that they are older in the east. This is the Santander Massif. That they are older in the east and they get a little bit younger in the west. The oldest ones are out here. Right, so more chemistry. And this is this is these red rocks and the blue rocks, okay? The chemistry. And it's basically just the squares, all these squares. And all we can see, it doesn't matter about the axis, forget the axis. They go straight into this metaluminous field. This is arc. This is classic continental arc. To give you a comparison, the Triassic rift was here. This is arc. Okay. Remember the chemistry, it's classic continental arc. The rare earth elements, classic continental arc. Okay. I won't explain why, there's no time. It doesn't matter. It's mainly a calc-alkaline continental arc. The Azafran, the Abitagua, the Zamora. That's not ambiguous. But now let's look at the Alau. Very enigmatic, very frustrating, very interesting series of rocks. Here we see this mainly mafic volcanics. Here we see photographs actually taken in the Pastaza, just at Baños, down under the bridge at Baños. We see mingling here between mafic lavas. And the controversy for the Alau is the British survey said that this is an interoceanic arc. It's not true because there are actually metaturbidites. There are sedimentary units that intercalate or lie between these mafic lavas. And here's some data from the sedimentary units in the Alau. These are the dense minerals, and actually they're full of zircon, monazite, tourmaline, apatite. This is not an oceanic environment. These are derived from a continental crust. This is a continental arc. And also the zircons in the sediments give this zircon, these are the crystallization ages, give this age spectrum, which has a Sunsis, a Brasiliano peak, a Sunsis peak. It's full, the Alau arc in the sediments is full of detrital zircons that came from the continent. This is a continental arc. So some chemistry for the Alau and the Quebrada Grande. It's the green colors, okay? These two green colors. Very, very, very metaluminous. Classic arc. This was the Jurassic. These are the early Cretaceous Alau. We think it's early Cretaceous. For comparison, this was the Triassic rift, okay? In this tectonic discrimination, we're looking at the green colors. Remember, for the Alau and Quebrada Grande, it's continental arc. And what you see here, the chemistry of the Alau and the Quebrada Grande, it's arc. It's just not very, very enriched compared to the Jurassic. It's much more mafic. It's less fractionated. I want to say something important here, and that is that sometimes you get some Alau which plot up here in seamount or in morb here, not in the arc. And this is simply because when you go to the Alau, it's structurally very, very complicated. And it's easy to pick up basalts in this area and think they are Alau, and they are not. They are peltitec. So the Alau is arc. The Alau which plots up here is not actually the Alau. It's not even arc. Okay, we're building a story. The last suite of rocks the second last suite of rocks I want to talk about are this very thin sliver, this dark blue color here, and there's a little bit here. In Colombia, it's the Archaea and Barragan. Here it's the Raspus. And these are amphibolites, blue schists, eclogites, high pressure, low temperature rocks. And they've been dated by different techniques. I'm not going to go into detail, but you can see here ARARPHN. That's an argon-argon date of a high pressure white mica, a phengite. Lutetium hafnium of a garnet. All these complicated radiometric dating systems which give different ages. I'm just going to go straight in and tell you what we think. We think that all of these units here and the Raspus are the same rocks, they're the same unit. They form part of a subducted slab which reached peak metamorphism at this time. That's what this date records. And these dates, the younger dates, all record when this was being exhumed, when the subducted slab was being exhumed. So this is peak burial or peak subduction burial of the slab forming the garnet, and these are exhumation dates. So we have to bring this into the Cretaceous story too, because these are early Cretaceous dates. And we also have the Peltatec unit in Ecuador, which I'll talk about a bit later, is 135 million. I'll talk about that later. So this is the chemistry of these high pressure, the Raspus, the Archaea, and the Barragan, the high pressure units. This Colombia, this is Ecuador, and the only message to get from this slide is that they are oceanic crust. It's essentially mid-ocean ridge basalt, maybe with some seamounts, but it's oceanic crust, which was subducted to high pressure, low temperature conditions and exhumed. And it occurs all the way up into Colombia. Okay, so now let's summarize this. Back to this section. Remember, this is an arc unit, this is arc, this is arc. Okay, this is this Peltatec unit, which I did not speak about a lot because of time. It doesn't matter. Remember, I told you that as we go this direction, the arcs get younger and younger and younger. And this is extension, younger and younger and younger. This is extension through the Jurassic and particularly the early Cretaceous. This is thorium cobalt. It's just a diagram that can distinguish lithologies. Okay, you see basalt, rhyolite, okay, lithologies and fractionation sequences. The details aren't important. What is important is this is the direction of these red, blue, and green arc rocks getting younger in this direction. So the rocks get younger this direction, but they also become from high potassium calc-alkaline to tholeiitic in this direction, too. That's what this is showing, okay? We also see when we go in this direction, when they get younger, that this follows this arrow, this epsilon neodymium. This just tells us that when we go this direction, these arc units from the Abitagua to the Azafran to the Alau have more and more mantle component in the source. Or you can think less and less crustal component, but they are continental arc rocks. This diagram says exactly the same. As we go in this direction, the neodymium value on this axis goes up and up and up. That's because as we go this way, when they get younger, there's more mantle component. And this graph says exactly the same thing, but now it's hafnium. It's just very solid evidence that when you go in this direction, there's less and less and less crust as we get younger that's contaminating these arc magmas. That's extension. Now, the last thing, I want to talk briefly about this. Those of you who've read the British Geological Survey book on the Cordillera will have heard about the Guamoti terrain or the Chaucha terrain, and that is these quartzites and slates which exist to the west of this Peltatec fault, to the west of all these arcs, this very anomalous piece of continental crust. And the British survey said this is an exotic allochthonous continental fragment. And this is not true. So what we did is we took some samples, some sedimentary rocks here. They are mildly metamorphosed. Some samples, some sedimentary units. And we took samples of sedimentary rocks in these arcs, and we looked at the zircon, uranium lead ages. Remember, these are detrital zircons. This is the data from the Chaucha, from here. And all of this data, is from here. So different sides of the Peltotec fault. And the message is, this data here, which are zircon, uranium, lead ages in histograms, look identical to the zircon histograms here. The bottom line, these are the same rocks as these. Okay, this is a piece of the continental margin of Ecuador, which was rifted off and reaccreted. So I appreciate that was a lot of information, but this is the final tectonic model for the Jurassic early Cretaceous. So in the Jurassic, we have a continental arc. In Ecuador, of course, Abitagua, Zamora. It was fairly static. It's not very deformed, high potassium calc-alkaline, of course, associated with some very large gold deposits in the south of Ecuador. But then at 145, the arc migrates towards the ocean. Right? And also the arc which forms, this is the Azafran, is very deformed. It was being intruded sin extension, during the extension. This is not deformed, this is very deformed. So the arcs have gone younger in this way, the deformation is increased, and there's a stronger mantle component in the Azafran because the crust is thinner because of the extension. When we go younger again, this is Ecuador, this is Colombia. The extension which started here continues very, very significant and strong. So the Alau is out here. It's forming under a thinner and thinner and thinner crust. So the Alau has almost got an intraoceanic type geochemistry, but it's full of continental detritus. It's a continental arc through very thin crust. And in Ecuador, this continental material here, which looks identical to everything to the east, was simply rifted off. And this is the Peltotec unit, which formed at 135, 130 million years in between. This is transitional morb, if you like, mid-ocean ridge transitional morb. In Colombia, it's the same story. The Alau is here, except it's called the Quebrada Grande. In the Quebrada Grande, we have got geochronology. We know it's this old, but the age of the Alau is still a mystery. So this is hypothetical in terms of age in Ecuador, but not in Colombia. And in Colombia, there was probably less extension because we don't see out here continental fragments. And finally, the Raspas and the Barragan and the Archaea are this subduction zone here. So all these units here, go back to the map. These high pressure, low temperature units here in the Raspas, that is simply this subduction zone here, which is exhumed. Now, at 115 to 110 million years, we have thermochronological data, which I decided not to show you to try and save time. We have thermochronological data that tells us that at this time, all of these rocks were uplifted. So at this time, all of this extended and thin margin in Ecuador and Colombia was compressed at this time. And this is what exhumed the Raspas, and here the Barragan and Archaea, 115, 100, and 100, maybe 120, because when we look at the exhumation dates of those units, we see there are 123. These are the exhumation ages, 123, 112, 120. This is the exhumation of this slab. These units which are abducted onto the continent. So that's the story I want to cover. And then this margin, we think, in most of Ecuador and Colombia remain passive. And then the next part of the story is the Caribbean, but I'm not going to go into that part of the story. I will conclude. So to conclude, in the Permian, we had a continental arc along western Pangaea. In the Cordillera, we call it the Malacatos because it's exposed at Malacatos. We didn't find it anywhere else. And Ecuador is in the back arc. The arc is blocks which are now mainly in Mexico. In Triassic, at a big high temperature metamorphic event at 255, but you don't find that in Ecuador, that's in Colombia. But then during the Triassic, there was a big rift, which rifted off the Permian arc and transported it to southwestern North America or into Mexico, a big rift-to-drift transition. Then at this time, we had an active margin forming these late Triassic to Jurassic, the Azafran, the Abitagua, the Zamora, and at 145, 115, very, very, very strong extension, which detached the Chaucha. And this was all recompressed back together at this time, probably because, of course, the question is why. There's evidence suggests it happened. The question is why did it happen? We can hypothesize it happened because this is when the South Atlantic opened. Africa did not move. The accommodation was all taken by pushing South America into the Pacific Trench, which drove the compression. So I will finish there. Thank you very much. I'm finished. Sorry for not speaking Spanish.
Thank you very much for your presentation, dear Professor Richard. It's time for answer some questions that our published want to ask you. First question is from John Manrique. And the question is, do you think that the formation of the Triassic Rift could generate some mineral deposits type sedics or sedimentary exhalative deposits?
Yes, absolutely. Yes, the quick. I am not a geologist, but I would say yes, certainly. It was very hot, and certainly we know that when the mafic Triassic rocks were being intruded from the decompressing the mantle, that there was a lot of fluid movement as well. We know that because we can see that in the compositions of the zircons. In fact, the zircons are metamorphic. So actually the rift is a high temperature metamorphic environment and a fluid-rich environment. So I would think so. In Ecuador, the problem might be to find them or if they are preserved, because we looked a lot for, if there was a Triassic rift, there should be a Triassic sedimentary package as well. And in Colombia, there is, it's called the Payende red beds. But in Ecuador, the BGS mapped a sequence in the south, and I've forgotten the name. I know some people here know the name. It starts with a P. There is a Triassic sequence of sediments mapped by the British surveyor Nia Loja, but we could never find them. They're called a Pionza unit. So maybe a target to go to look would be in the Pionza unit, maybe. Would be interesting idea.
Okay, thank you very much. The next question is coming for George Toro. The question is about Chaucha terrain.
Right.
If you ratify the location and geodynamic meaning of the Peltetec fault or Peltetec structure, what will be the real composition and geodynamic context on the Chaucha terrain, continental or oceanic?
Okay. Very nice question. I could speak for many hours on this subject. So the Chaucha terrain, certainly the evidence shows that it is a detached piece of continental crust, which was once part of the Ecuadorian margin, which was rifted off and then reaccreted. It's not very exotic. The composition of the sedimentary rocks to the west and the east of the Peltetec fault is the same. So there's no reason to think that it's exotic to South America. Now, the Peltetec fault itself, at least for me, the Peltetec fault has every single rock that you can think of that's exposed in Ecuador, you can find in the Peltetec fault zone. It's just for me, it's a tectonic melange, which has a very long strike-slip history. It's exhumed the basement, so you find Tres Lagunas units. During the rift, you have 140, 130 million-year-old basalts. We recently published in the Tres Lagunas, there are 560 million-year-old basalts. In the Peltotec fault zone, you essentially find everything. For me, the Peltotec fault is not really a major suture. It's just where the Chaucha terrain was rifted off. It wrenched Ecuadorian basement to the surface. The Chaucha came back, closed the Peltotec basin, if you like. And that's a long, long, long-lived fault, and it's dragged or any rock type you can think of into the fault. So when people say the Peltotec unit is at 300 or 200 or 100, the only response is, well, which fault block? Because the Peltotec fault is many, many fault blocks, and every single fault block is different. It's just a melange of units.
I imagine that.
Yeah.
Next question is coming from Arturo Egues. He wants to say, hi, Richard, congratulations and regards. Two small questions. What kind of samples is your Permian rocks? Do you think one sample is enough to establish your model or Permic arc? If the arc continue on the Triassic time, why there are no evidence on the arc in Ecuador? Thank you and best regards, Arturo.
Okay. Hi, Arturo. Professor Egues, and thank you for the congratulations, Professor Egues. Okay, yes, the Permian is strange. I mean, we only found that one Permian rock by luck, by chance. No, I would normally never define an arc on one rock. But when you go into Colombia, we see more. And when you go down into Peru, Eastern Cordillera of Peru, you see a lot. So if you like, in the Cordillera Real, there's a Permian gap. Maybe it's not exposed, maybe it's buried, but it looks like there's a Permian gap in Ecuador. And this is why we think that the Ecuador in particular was in the back arc. Because when you go and look at the Mexican units, you find the Permian arc. And in most of the reconstructions of the Mexican blocks and Northwestern South America, will place those Mexican units offshore Ecuador and Colombia, where I also put them. So, no, if I only had the geology of Cordillera Real isolated, I would not have an idea what the Permian rock was significant about. But because I have Peru and Colombia, and in the context of Colombia and Peru and Mexico, that's why we think it's an arc. But no, I would not make an arc if I only had one data point. But we have more when we look in a larger region.
Okay, next question is from Dalton Herrera. Thanks for the conference, he says. My question is, which is the country or region that has the most chronological diversity?
Which country?
Yes.
Oh, wow. In South America or worldwide?
I prefer to say just in South America because...
I would say in terms of the published dates, in Colombia, you can go from 1.5 billion to today. In Ecuador, I don't know any radiometric dates. Maybe somebody can correct me. The oldest radiometric dates I know in Ecuador are 550 million. I would say maybe in Venezuela or Colombia, you might have the biggest range of radiometric dates. Argentina, perhaps.
Brazil, it's possible, Richard.
Yeah, in Brazil, you don't have the young units, right?
Yeah.
But but certainly in Venezuela and Colombia, you have 2 billion years of geochronological dates. Maybe there.
Thanks. Next question is coming from Angel Leica. He says, good afternoon, and he would like to know what is the age of the unit Guamote. That unit has the same age of the unit Chaucha? That's the question.
So, okay, so the only information, well, first of all, the sedimentary units, the quartzites and the slates do have fossils, ammonites, which have been dated to Jurassic. And also we have from those sedimentary rocks, zircons, which, but remember those zircons they are not igneous rocks, they are sedimentary rocks. So those zircons have been brought in by transport. So they don't date the rocks, but what they do is they give the maximum age of the rock, right? I don't have time to explain that in detail, but what the zircon uranium lead dates tell us is that they are consistent with the fossil dates, and they are younger. They are definitely younger than about 155 million. They're probably late Jurassic.
And Jorge Toro says, I visit the outcrop in the north side next to the Tungurahua volcano, in which we have some metasediments from Alau lithotectonic near to the bridge. I identify in these metasediments sedimentary structures similar to double math layers, usually from tide-dominated environment, and amplified double math layers, usually from deep marine environment. The question is, how to understand your continental interpretation for Alau terrain, and how to understand the occurrence of these marine sedimentary structures?
Okay. I think the best answer I can give for that is, so the Alau arc was certainly a continental arc in a tectonic sense, in the sense that it was the isotopic and geochemical data shows that it was intruding through continental crust first, but the crust was very thin, very thin. Okay, and probably most of the igneous units are submarine. So the Alau arc was almost certainly a submarine arc. So the environments would have been marine. I don't know how deep they would have been, but it was erupting into a marine environment. It wasn't a subaerial terrestrial oxidized arc. It was a submarine arc erupting onto the sea floor through thin continental crust. So I don't see a problem with having those marine sediments there. I would expect to have those marine sediments there, in fact. So that's a nice observation. I would say that's consistent with us. It was a very thin crust. It was submarine. You would expect to have these marine deposits.
Okay, and the last comment, I think, it's coming from the Professor Arturo Eguers. He says, you forgot the Alau history in your conclusions.
Oh, sorry. Excuse me. Did I? Okay. I think this is because the Alau always makes me very frightened because we tried to, I'm very confident with the Alau interpretation we have. I would be more confident if we get some geochronology, but we tried for 20 years to date it. And the problem with dating the Alau is we cannot find any zircons in the igneous rocks. And we looked at, I'm not exaggerating, maybe 200 rocks. And we also tried what's called the argon-argon method. We have a student now from EPN Quito trying to date the Alau with the argon-argon method. And we are getting dates which are much younger than its crystallization age. So they're not, the argon date is actually not telling us the crystallization age. So the Alau is still an interesting mystery, but that's not why I left it off the conclusions. I guess I just forgot. Sorry.
Yeah, I suppose that it's a comment, a very good comment, imagine. Thank you for answering all the questions that our attendance has. And espacio para que John Enrique.
Gracias, Vero. Voy a compartir la pantalla un momento. Richard, congratulations for your presentation. We have a fine for you talk in this conference. We send the certified signed net weeks. I read the certificado al Dr. Richard Spiking por haber participado en calidad de expositor en las conferencias de Geociencias organizadas por el Departamento de Geociencias y la carrera de Geología, llevada a cabo el 27 de mayo del 2021 en la Universidad Técnica Particular de Lo. We have, sorry, okay. We hope to see you soon in Ecuador, Richard, and we're very happy for your presentation in this conference.
Okay, well, thank you very much for your interest in the work and inviting me, and for the certificate. I enjoyed a lot the discussion, and so thank you very much.
Thank you very much for helping us with your conference and explain us everything that you know. Muchísimas gracias a todas las personas que nos han acompañado en esta tarde. Los invitamos para que nos sigan acompañando el 3 de junio. Vamos a tener el tema la sismicidad en el Ecuador y su realización con la tectónica, la cual va a estar a cargo del PhD José Tamay Granda. Los esperamos y que tengan un excelente resto de su tarde. Gracias.
Mi nombre es Yandri Anthony Gualán Velázquez y actualmente estoy estudiando Ingeniería en Geología. Decidí estudiar Geología en UTPL porque es una universidad muy prestigiosa y reconocida nacional e internacionalmente. Además cuenta con una infraestructura de calidad. La UTPL brinda becas e intercambios estudiantiles, como también tiene su biblioteca totalmente equipada para solventar y satisfacer nuestras necesidades académicas. Mi experiencia de estudiar geología en la UTPL ha sido muy enriquecedora. La universidad me ha permitido explorar, conocer más acerca de la carrera. Siempre me han gustado los aspectos de la naturaleza y la carrera me da una visión más concretamente en lo que es la formación y la creación de la tierra, haciendo de esta una carrera cada vez más interesante. Recomendaría estudiar en UTPL porque te permite realizar prácticas preprofesionales a través de las cuales adquieres experiencia y puedes desenvolverte mejor en el ámbito laboral. Además cuenta con profesionales de cuarto nivel, maximizando así nuestra calidad de aprendizaje. Si te apasiona explorar sobre las riquezas de la tierra, ven y estudia en la UTPL. Decide hacerlo.